Okay, as we start off today, do a couple of applications of Faraday's law. So we're gonna go back to chapter 31. Page 869 there. And we're gonna talk about one application is a ground fault interrupter. So this is basically a device that will turn off an appliance if it's receiving too much current. So this is like a, it interrupts the current. It shuts the device off if the current flow to that device is more than it can handle. GFI for short. So let's say you see the picture there. We have two coils from the outlet, and let's say this is our circuit breaker. Then we have these two wires that are coming from the circuit breaker to the appliance. Let's say that this would be the direction of current 1, and then we have current coming back from the appliance. Call it current 2. Then part of this device will have a solid iron ring with a coil attached to it. So this is this coil here, the circuit breaker there. This is what's known as the sensing coil. And we have alternating current, or AC. And so we have these two wires. One going to the appliance, and wire 2 is coming back from the appliance back to the wall outlet. So if everything's good, even though there's the amount of alternating current in wire 1 to the appliance is going to be the same as wire 2, if in that case everything is in equilibrium, that the sum of the changes through this coil, the sum of the changes of EMF through this coil is basically going to equal 0. So everything's going to be in balance, in equilibrium. The magnetic fields from wire 1 and wire 2 cancel each other out, so everything's good. But if for some reason that an appliance gets wet, or there's a surge from whatever source, then it's possible that there's going to be an uptake in the current from, let's say the appliance was it's over here and it's compromised. Let's say it got wet. Well, there's going to be a surge in the current in wire 2, and if there's more current coming back in wire 2 than there was from wire 1, there's going to be a change in EMF in this coil, which induces a magnetic field well, it's going to be a change in the magnetic field. But this current here, if it's larger than 1, it's going to induce a magnetic field around this coil that's larger than coil number 1. That magnetic field is going to produce a change in the current in this coil. So when that current changes, that signal is sent back to the circuit breaker here, and it shuts the appliance off. So that's all because wire 2 was greater than wire 1. This wire induced a magnetic field in this coil. That magnetic field, that change in magnetic flux through this coil induced a larger voltage, say current, in this coil, and it was sensed by the circuit breaker. The circuit breaker shuts off the appliance. And so that's just one example of the application of Faraday's law. So that's the ground fault interrupter. So this ground fault interrupter, it interrupts the current going to the appliance, and so it doesn't blow up or anything, overwork, short circuits or something. So that's one quick example of Faraday's law. So a second example is, sound production in electric guitars. So say we have a guitar string, and there's like a pickup coil on part of this string. So let's say, here's a pickup coil. And this pickup coil is placed near the vibrator. So this is the guitar string here. So this is the part of the guitar string. And inside of this pickup coil is a magnet. It magnetizes the string inside the coil. So we have a situation where we have a coil of wire, and then there's a magnet inside the coil. This magnet inside the coil magnetizes this string that gets sent, or the signal gets sent to an amplifier. So yeah, this magnet's inside the coil, magnetizes this part of the string. And as this string vibrates at a particular frequency, there's going to be a change in magnetic flux through the coil. That change in magnetic flux is going to produce a current that gets sent to an amplifier. And then the amplifier signal goes to the loudspeakers, and we hear that tone, amplified through the loudspeakers. All because this vibrating string produced a change in magnetic flux through this wire, because this is a magnet. And if you will, part of, the string, you're plucking the string, and that frequency gets, causes a change in this magnetic field. It vibrates the magnet, and this changing flux inside creates a current that gets sent to the amplifier. The amplifier goes to the loudspeaker, and you hear that F sharp very loudly. So again, another application of Faraday's law of induction. It's all about the principle of changing magnetic flux through a coil. Once you do that, you've created a current that you can redirect anywhere, in this case to an amplifier, to loudspeakers, and you hear that sound. So there's two examples that wrap up chapter 31. Let's go to chapter 32, the principle of inductance. So we're going to talk about self-induction. And the basic concept of self-induction is that when you connect the circuit together, you have a battery, wires, a resistor, and all that good stuff. You turn the circuit on, or you connect the battery to all those appliances. What happens is that the current doesn't increase, it doesn't get to its maximum value instantaneously. It takes time to get up to its maximum value. Short amount of time, but there's a time interval. As the current goes through the circuit, there is a magnetic field that's created, through the circuit. But as that current increases through the circuit, it sets up an alternating magnetic field. And so basically, it sets up a magnetic field such that it creates a current to go in the opposite direction. And the reason why that happens is because the current is changing through time. And so as that current is changing through time, it creates a new magnetic field that creates a current to go in the opposite direction. So the circuit itself is inducing a new current to go the other direction opposite the original direction. This is a process called self-induction. The circuit induces its own new EMF, which sets up a current and goes in the other direction. So self-induction it happens as a result of a time-varying current. The time-varying current in the circuit produces an EMF opposing the original EMF, since the original current intrinsically varies through time. Anything that has a fluctuation, there's a change. If it's not static, as in the case of a time-varying current, it's going to automatically set up a new magnetic field whose current that it creates is going to go to oppose the original current. So I'll give you a picture of that in a moment. Since that original current changes through time. So let me give you a little bit of a mathy deal here. The original time varying current, the current changes through time, eventually creates or induces a new EMF, and that new EMF creates its own current that goes in the direction opposite the original current. So DIDT, this will be induced. So that's the basis of the inductor or induction, that the circuit, without any other aid, creates a new current within it without adding another battery or anything, anything else. So this is the basis of self-induction, or basically we're going to be taking a look at a new circuit element called the inductor, because an inductor is going to be a circuit element that causes this to happen. Okay. So in section 32.1, entitled Self-Induction and Inductance. So let's say we have a circuit that looks like this. So we have an open switch here. Right, and then so a resistor, it's our battery. And so this is a switch. Obviously right now there's nothing, current's going to flow because we have an open path. Once this switch is thrown, we have current that's going to, flow in its conventional direction. That current produces a magnetic field that, curls, if you were looking at this as the plane of the page, it comes out of the page. So it's going to come out and then go back in, out to in. So this is the magnetic field that's set up by this original current. So we can just call this our original magnetic field. Well, since this original current is varying through time, it sets up a new magnetic field that creates a new EMF or a new current that goes in the opposite direction of this original current. So the new magnetic field is going to be, if this was out to in, the new magnetic field is going to be in to out, right? It's going to, go in, let's say, in this direction. So that's the induced magnetic field, all because this original current is changing. And so it's going to set up a magnetic field whose direction, and the reason why it's this way is because if you use the right-hand rule, your thumb is going to be pointing down the current, or down the circuit. It's going to be pointing in this direction. So this is a operation of a circuit called self-induction. It induces its own new current just because the original current is changing. So we have kind of a sluggishness of this current. So the current's still going to flow from positive to negative, but it's going to be slowed down by this new EMF. And that should make some sense to you, because before the switch is even thrown, there is nothing happening. So when the switch is thrown, the application of this new EMF is to create a situation that cancels out that original current, basically bringing the whole system down to zero, because that's what it was in the first place. So it's trying to maintain the balance that it had in the first place. So this arrow here would be the induced current. That's equal and opposite the original current, or you can just say the new EMF is equal and opposite the original EMF. Add them together, they sum out to zero, and that's what it was before the switch was thrown. So this was it's open and now close, switch, and so we get this operation. That's at least a picture of this circuit inducing a new current all by itself. No extra coil, no solenoid, no extra battery. It did it itself. That's why it's called self-induction. So we'll write a little bit regarding that. So this original time varying current so it creates an original magnetic flux, magnetic field that curls around. It's not really a flux because it's not going through anything, so I'll just say it creates its own magnetic field. Let's see. And so that was the original magnetic field. But over time, since this is fluctuating, the original current is fluctuating, it's going to set up a new magnetic field that curls in a direction. The direction of this induced magnetic field is going to be from outside to in this plane here, so that the EMF or the current that it sets up opposes the original current. So the original current sets up a field that goes from out to in and back around. The new magnetic field will go from in to out. It's just the opposite. If you use your right-hand rule properly, you will see why the original magnetic field is this way. Your fingers are going to be curling into the plane. Your thumb is going to be pointing up the circuit. And then the induced magnetic field It's going to be, your finger's going to be going into the plane of the circuit on the inside here, and your thumb is going to be pointing down. So again, just repeating that. So we get that picture. So that's our original magnetic field that's created by the original current. Any questions on that? So the circuit has induced a new EMF all by itself. Self-induction. There's a general term given to this new EMF. It sets up its own current. New EMF is called a back EMF. Now I like to just generalize this EMF. Yes, there's a voltage difference that goes the opposite direction, but there's a current that's flowing the other way. So we can just think of it as just a current that flows towards the positive terminal of the battery, as opposed to the original current that flows from the positive terminal. Called a back EMF because it goes backwards, or a negative direction. We say negative because conventionally from positive to negative terminal is a positive conventional current, and anything that goes the opposite direction is deemed negative or back EMF. So this created or induced EMF, the back EMF. Given another name. Self-induced EMF. The circuit did it all by itself. Now, this self-induced or back EMF is proportional to the rate of change of the current in the first place, the original current. And let's say that we had any arbitrary loop of wire that's going through or where the current is going through. The magnetic field that gets created through this loop of wire. So that's it. We have like a just arbitrary coil, a solenoid. So the current is going through in say this direction. The magnetic field is going to be it's going to be, you know, in this configuration, it's going to be coming out of the page and circling around. It's going to go out to in. Since this is time varying, there's going to be a new magnetic field that creates a new current going backwards, back EMF. And that's going to be going in to out. So it's just opposite. The sum of all these changes, 0. There's a conservation of energy, all by the circuit just on its lonesome, by itself. So this is going to be in to out. So these are field lines in and circling around, out, and it's sort of like this on this side. If you can imagine this curling backwards, I know it's probably a little bit hard. And this one here will just be in that direction. First coming out towards you, and then goes back into the page and back around. I'm trying to make these dots. So something like that. So this back EMF, proportional to the rate of change of the original current, so like I was saying, back EMF proportional to the rate of change of the original current, and I'll just continue it here. And for any loop of wire, and I just do an illustration there. We write the back EMF as EL. This is basically the induced EMF. L is going to stand for inductance. See here, negative L di dt. Very similar to this induced EMF, which is equal to negative N d phi b dt, which is Faraday's law. It's the same principle, really. That this is saying that the induced EMF is going to create a magnetic flux to oppose the original flux. The induced EMF here in a self-inducting circuit is going to create a current that opposes the original current. This opposition encapsulated by the negative. It's going opposite. This is your back EMF in equation form. This is your induced EMF that creates its own flux, changing flux the opposite direction. They're all proportional to changes. If you have no change, you will not get any created EMF, as we can see in the equations. There has to be a rate of change that opposes the original change. L is going to be the inductance of the circuit. N is the number of loops of wire, but the physics is really the same. This is for magnetic field, this is for current. The inductance case, we have a changing current. Remember back in chapter 31, we were doing changing magnetic field through a wire. So this is just another way of seeing that there is an interdependence between electric fields and magnetic fields. And we're going to see that encapsulate or come together when we talk about electromagnetic waves. The rate of change of the changes of electric field and magnetic field, if you will, happens at one particular speed of light. And all parts, there's different parts of the electromagnetic spectrum. Visible light, X-rays, microwaves, gamma rays, and so forth. So when one of those fields changes, it creates another changing field. A changing magnetic field will create a changing electric field and vice versa. They keep looping back and forth on each other. And we can start to see that right here in those two equations and other equations for Faraday's law, and intuitively. You get a battery, make a circuit out of it, connect it up. Once it's connected, you switch it on, or, if you have a switch. All circuits then have their own inductance. The current is not going to reach a maximum value instantaneously. So in that case, it initially creates its own, there's a magnetic field created by the current itself, but since it increases over time, there is another magnetic field that gets created to create its own current that goes backwards. And the net result is 0. The sum of the changes of all of that, 0. It's beautiful harmony. You track it all the way. So that we got this. And back to this equation. All right. Where L is a proportionality constant called the inductance.
Mr. Kelly, I have a question.
Yep.
Does a similar process happen when you open the circuit?
Yeah. When you open it, the current is going to go back the opposite way.
The original one, right?
Correct. So now when the switch is open, the current goes backwards, and so now we have a decrease in the current. Yeah.
Yeah. Okay.
So okay. So 1 second, I'm gonna pause right here. Come back. Okay. Sorry about that. So let's continue on with the rest of this. All right. So let's say that we had a part of the wire, part of the circuit before. I was showing that we could have a part of this circuit to have a wire, coiling around one part of the circuit. If you do have this, there's going to be current going through the coil, and it's going to produce its own magnetic field. And as the current is changing, it produces a new magnetic field that goes the opposite direction, which creates a new current. And we call this device an inductor. Now, with this loop of wire, or you can say it's a torus or solenoid, whatever we want to say. So considering a torus, like the solenoids that I have in class, and we run current through those. If current is time varying, then we're going to get magnetic field through the solenoid. So that's why the magnetic field this time is going to be going linearly as opposed to curling, at least through this torus or solenoid. So it doesn't matter what you're sending through. You're either going to send magnetic field through, it creates a current, or you're going to send current through, it creates magnetic field, and vice versa. So considering a torus or solenoid of n wire turns, so we know that EL equals N, and this is Faraday's law. And we know that the induced EMF in terms of inductance is equal to negative L di dt. in solving for the inductance, we have because the negatives go away. And the DTs also go away there. So we can just look at the inductance at one moment, or the inductance of the entire circuit, because, you know, realistically, the current is changing throughout time over the entire circuit. But if we look at, say, a so-called instantaneous inductance, or inductance just quantitatively speaking, L equals N phi B over I. And so this is basically the quantitative description of inductance in terms of the wire turns of the solenoid. And yeah, in terms of the wire turns in the solenoid, so we solve for the inductance, which we get from our new inductance equation here. So this new EMF that's set up by a new magnetic field is going to oppose the direction of the original current. And so we can solve for L using those two equations, and we get this. So that's our inductance equation. And inductance is going to be based on the geometry of the circuit, because remember, phi B is going to be BA cosine theta. So it depends on the area. So that's why it's based on the geometry of the circuit. If it's planar, if it's cylindrical, if spherical, then this area changes. Based on geometry of the circuit. So that is that there. And then going on. And of course, we can also write the inductance L as L di dt. And that just pretty much illustrates the inductance of the entire circuit. And this is basically at a moment. And yeah, so basically all circuits have their own inductance. Oops. All circuits have their own inductance. And that was a good question by Edward. If you open the switch, what happens? Yeah, the current's going to go the opposite direction. So we're going to get even more increase of the back EMF. So either way, we're going to get, you know, the sum of the changes of the EMF is going to be zero nevertheless. So and that's fine. So it all pretty much works out. The main thing to keep in mind is that both EMFs, the original and the induced one, net zero. Okay, so now there's another property of the circuit called resistance. That's the ability of the circuit to resist, as it were, your current. And is symbolized by the resistance, symbol there. And resistance is a proportionality between voltage and current. And we also know that inductance, negative EL, dt. So inductance is like a type of resistance. You know, this new self property of the circuit that is either naturally produced without a resistor or with one, or with an inductor, that is going to necessarily slow down the original current. So it acts as a type of resistance. So both of these are oppositions to a change in current. But the difference between these, this is going to, this function is to get your current down to a small value as much as possible, depending on the orientation of your resistors. And this one is going to resist the original current, but it sets up its own. So it's not going to, it's not going to result, or its primary function is not to eliminate the current, it's just to go against the original flow. All right, so there's oppositions, whereas a resistor doesn't do that, to changes in current. And unit of inductance, called the Henry, after Joseph Henry, who came up with the idea or proved that circuits create their own inductance, their own EMF. After Joseph Henry, so the unit of inductance is called the Henry. We denote as H. And so 1 Henry is equal to 1 volt second per amp. So if we look at this, and we do, reciprocate this as a dt, we integrate that to t, so volts second per amp. So that's it. Okay, I think we can pause here and do a sample problem. All right. Okay. Section 32.2. We're going to take a look at different combinations of circuits besides just resistor circuits with capacitor. We've already seen RC circuits. Now we're going to look at RL circuits, resistor inductor circuits. So let's say we have a circuit that looks similar to the one in this section. So we have this configuration. This is the second switch, first switch open. And then we're going to take a look at the symbol for an inductor. This is basically a coil of wire, solenoid or torus of wire. And then come all the way down. And so, all right, so again, positive, negative, so battery. And this is going to be L for resistor, RL circuits. So the basic idea here, obviously we can't get a connection with this switch 1. But if we just had this configuration here, S2 being closed, we still have a circuit formed by this battery. And it's going to be time varying current going one direction. It's going to be, let's say, okay, let's just start from scratch. If S1 was closed here, we'd have a circuit going conventionally like so. And then if we open this, we have a back EMF going through. So we would have, this would be a situation where we could, facilitate the self-induction in this current. So we have this current going the opposite direction when we open S1. And this happens when you open S1. And then if you close S1, obviously there's going to be a current that's going to be the easiest case. We close this, close that. This current is going to be time varying. It's going to have its own magnetic field that eventually, by its nature, by the fact that it's varying through time, it's going to create a new magnetic field through this coil of wire that's going to resist the original current. So if this is original, again, this will be induced. And that's the easiest case. If S1 is closed, you leave it open, we go backwards this way, and then we'll have, and then this now becomes the induced EMF, and this is the original, if you will, because now current is going to go the opposite direction, as we saw in the case when we are discharging a capacitor, for example. So, you know, either way you look at it, this is just a configuration to kind of give you more inclination as how this circuit can induce its own current, you know, that opposes the original. So close this, time varying, induced, open, original, time varying, and you know, we just switch the directions. Induced will be this way, and then the original, or this back EMF will go towards S2. So that's just another circuit case. Now, general features of this RL circuit. So this inductor, you know, it's basically, let's say if we had a circuit, has a coil of wire, torus, solenoid, has a coil like a solenoid. So the inductance, of the coil prevents the circuit from basically getting out of hand. So we're going to get a situation where if we close this first case, you know, S1's closed, right? This induced EMF is going to slow down the original flow. So there's no rapid increase or decrease in one moment. It's going to, you know, kind of degrade over time. The current's going to increase or increase over time. Or even decrease, right? So yeah, but so that's the nature of the inductor, is to prevent simultaneous increase or decreases in current. So with induction of coil prevents circuit, from increasing or decreasing at any instant, any moment. The symbol for the inductor is just a coil. Now we're going to be looking at the inductance in the inductor as opposed to the rest of the circuit, because the circuit is going to be a simultaneous inductance all throughout, but we're going to consider the inductance of the rest of the circuit negligible. It's like air resistance negligible. We're just going to concern about the inductance in the coil. So the inductance of rest of circuit negligible. So all circuits, no matter you open, close, whatever, have some inductance. It's pretty weird, you might think. I think that's pretty weird. It kind of sort of counterintuitive, but circuits have some inductance, as we saw earlier in the previous section. So let's say that we have a coil of wire. It has original flow of current. Magnetic field is going to go through this coil. That's a result of this changing time varying original current. Well, that original current is going to be opposed by a new or back current, back EMF, whose magnetic field is in the opposite direction of this equilibrium, right? So we're just talking about the same stuff again and again. Since the original current it increases, we are going to be opposed by this increasing current originally by a new current that goes opposite direction. How does that current get set up in the opposite direction? By a changing magnetic field to oppose the original magnetic field. So it swaps out. So we're going to get this situation, induced current or EMF, switching of polarity, not physically, but inductively. The polarity goes from positive to negative, negative to positive, goes the opposite direction, negative current, goes against the conventional. Induced magnetic field to oppose the change, sum of the changes is 0. So the inductor, as we saw in the equation form or from the experiment, leads us to the equation. And in that equation, we see that the inductance is proportional to the number of turns of this solenoid. So this is why we approximate the inductance in a circuit, or we look at the inductance of the circuit at the inductor as opposed to the rest of the circuit. So the inductor, like I said before, causes the current to be sluggish, right? It kind of slows it down, degrades it over time. Or as the original current reaches its maximum, it takes a while to get up there based on the new EMF. So it's a sluggish increase. And we're going to see just what that looks like graphically after we solve, what is the current in this RL circuit, look at it graphically, do a time rate of change of current, all that good stuff. So anyway, okay, so put it all together. So the inductor causes the current in the circuit to be sluggish, as it were. Something slowing it down, impeding it. And it's using it in the English sense, and we're going to talk about impedance physically when we get to alternating currents. So now we close the switch and all that good stuff. S1's closed. Can we quantify the current in this circuit? Quantify basically, quantify the current through this RL circuit. Well, starting at the battery, that's the source of the voltage. Using Kirchhoff's rules, we're going to see that there's going to be a voltage drop across the resistor as IR, and there's going to be a voltage drop across the inductor as negative L di dt, which we saw before, because E for the inductance E is negative L di dt. And Kirchhoff's rules, the sum of all of the voltages is going to be equal to 0. So we have to, let's find the current in this RL circuit. Well, one way we can solve this first order differential equation is make a substitution. So this is what is known as a first order because this is the first derivative, if you will, and the second order would be d squared I dt squared. You know, this is a first order differential equation, or ODE for short. We have first and second order ordinary differential equations, ordinary, and then we have partial differential equations. You have to use separation of variables to solve those guys. So let's let x equals ER minus I. And the reason why I'm doing that, just for simplicity, we divide everything, divide this term here by R, and we get E over R minus I. And then dx is going to be equal to negative di. Just to get everything in terms of the one variable easy to do, make this substitution, and once we get a solution with the substitution, we back substitute what this is to get the final function. Therefore, this becomes x plus L over R dx dt equals 0. Hopefully you can see that. You know, do I divide everything through by R, yeah, everything. L over R, yeah. So, R, there we go. Okay, so then dx, because the thing, you know, you see the pattern, number of ways of thinking about first order differential equations. The way I like to think about them, I'm always going to get some kind of expression where whose integral is going to give me a natural log. So I'm going to have some d variable over that variable, you know, because it pretty much is going to come out to be that waveform, or this ordinary or partial differential equation. But again, that's just, you know, everyone's different approach. So dx, my left side, and I have, you know, everything else. So I've got negative x over here, and then I just divide through that by R over L dt. Can you guys see that substitution? I subtracted x over here, and then the dx. And in order to get the dx, I have to do the reciprocal, R over L dt. Get all the x's together and everything else on the other side, dx over x. Why bother with the minus sign? Leave the minus sign over there. R over L dt. And I think we see where this is going from previous. So we're gonna have definite bounds from some original position to x, dx over x. And then this is gonna be negative R over L. And it's gonna go from time equals 0 to whatever. Natural log of x minus natural log of x naught. And this is going to be, this integral is negative R over L t. And then this becomes a natural log of x over x naught, the natural logarithm rule. There's this. And so we divide both sides by natural log. This becomes x over x naught. This becomes e to the minus R over L t. X then is equal to x naught e to the minus R over L t. Now that's our expression with this substituted variable. And I guess I'll continue. Since x is equal to e over R minus I, we have e over R minus I equals e over R, because x naught is going to be, you know, this original E over R, E to the minus, from here, R over LT. And I think we can see where this is going. If we're solving now for I, I is a function of time because of time units. Then we'll see how current changes. So I is going to be equal to E over R, 1 minus E to the minus R over LT. And you can see this similar to an RC circuit where this would be, I think we had Q as a function of time equals CE, 1 minus E to the minus, what was that expression we had? 1 over T over RC, I believe it was. But it's very similar. And so we have another time constant such that when T is equal to the time constant, we're going to get a value of this current that's going to be 63%, just like in the charge case. At some point when the circuit reaches its time constant, the current in this RL circuit is going to be 63% of its maximum, just like we have for the RC circuit. So that's why it's a constant. No matter the value of R and C, or no matter the value of R and L, at some point, you're always going to be 63% of whatever the max. And the max is an asymptote. So tau L over R, time constant. This should be pretty cool to you because we're getting the mathematical formulation of what's going on in this physical circuit. What's happening to it? What's happening to the current? Well, it's getting to a max. Yeah, there's a back EMF, but it's gradual due to the inductance of this inductor, this back EMF. So it's not an instantaneous turn to a maximum value. It's gradual, it's sluggish. Get it? Time constant of circuit. And so we can write this as E over R, 1 minus E to the minus T over tau. Because tau is L over R, then this will be 1 over tau. Cool beans? Yeah, pause and consider that. So yeah, so this turns out, we have, okay, now you have this mathematical result. Let's go ahead and graph it. So we have current versus time in an RL circuit. So it's going to have some maximum, some asymptote here. And then it's going to gradually reach its E over R based on the EMF, the back EMF through the inductor. So let's say when T equals tau, we have 63%. Of E over R. And of course, for any values of R and L, that's why it's a time constant. Now, the next part, we're going to see how the current changes. So we've already seen when we discharge a capacitor, this time we're going to be changing the flow of the current, like I just illustrated at the top of this section here. When we switch, let me go back. Okay, yeah. So now when S2 goes here, and even if this is closed, so our current is just going to, it's going to just flow this way because this is not going to be This part is going to be open, this part is going to close. And so right now we should have some appreciation that the current is going to decrease over time, but there's going to be an EMF back. Take the inductor out, instantly zero. Inductors there, and gradually zero. So now I think and I hope that we have full appreciation for the circuit diagram. In the first case, the current is going to increase gradually to E over R. At some point, RL, when the time constant reaches R and L multiplied, it reaches 63%, and then we're on our way to the max. And it's never going to, it's going to limit as T goes to infinity. It's never going to reach the max because of this inductor. Now, the second part, we're going to see how current changes as we close this part now, go from A to B. And it's going to only use this. This is unimportant. This is going to switch directions. And we have the EMF switches directions. And so now we have a gradual decrease in the current. And I'm going to have you do that as a problem. But 1 second, I think there's some drums in the back. All right. All right, I'm going to black. So let's see how the current changes in an RL circuit. So we're basically going to disable the battery, change the switch from A to B in that other circuit, and the current flows the opposite direction. EMF is going to now change directions as well. Why? Because there's an inductor. So let's take a look at I as a function of T, E over R, 1 minus E to the minus R over L T. And we're going to do a rate of change of this entire deal for this function. This first term goes away because there's no time dependence, and then this the second term is, we're going to have the derivative of that would be epsilon, or the EMF voltage, over the inductance, E to the minus R over L T. So we're doing the time rate of change of current for that function, and we get that. So we're tau, and tau is L over R, and so this is going to be T over tau. Therefore, we can write this as d I dt E over L minus T over tau. So at T equals 0, it's going to be maximum. And as it goes to infinity, it's going to go to 0. Don't know how familiar you are with that, Edward, intrinsically, but you will remember we talked about that with the RC circuit. So it's the same relationship there. Just as an RC circuit, the current's going to die off to 0 as T goes to infinity. So the same case here.
Oh yeah, it approaches, but never reaches to that value.
Yeah, but my point was, is like, just being able to derive that when T goes to infinity, because e to the minus infinity is 1 over e to the infinity, which is 0, so the whole thing is 0. And so as T goes to 0, this dies to 0, or trends towards it, as you said, definitely. And as T is equal to 0, 1 over e to the 0 is just 1, so E over L is the maximum at T equals 0. So, and it slowly dies off, slowly die off because of back EMF, the opposite direction of this current that's now going in opposite direction. So this is going from, let's say, negative to positive. It's just going the opposite this natural or conventional direction. EMF is now going to go in the direction of conventional current. And that's what's causing the gradual decay. Take the inductor out. and we have an instantly zero current. It's just going to be a negative slope, negative x. And this is an exponential decay. So I'm not gonna, write down the S2. I think we, described what was going to happen. So if we now make the switch from A to B, we take the battery out of the situation. So we basically, remember originally we had this. And then when we would switch, we take the battery out and the current goes in the opposite direction. So this is not going to be a voltage drop, but a voltage gain. We're just changing direction. So this just becomes IR plus LDI dt equals 0. Now what I'd like you guys to do as an exercise, let's see if you can derive that equation 3210. And we'll come back and do it ourselves. Great. So let's derive that. So we started off with this here. And again, we want to get the rate of change of the current. So we want to have this on one side and other stuff on the other side. So this is going to be di dt equals minus IR. And then if I just want di, and then this is just going to be negative IR over L dt, di over I minus R over L dt comes out to be the same. Again, remember, we're going from a maximum current, I'll just call it big I to little I, di over I, R over L dt, natural log of I 2 natural log of capital I. Because remember, we're discharging technically, we're just reversing the direction of the current from a max to a min, going towards 0, right? And then this is going to be R over L T, log of I over big I. That's e to the minus R over LT. And that just becomes little I of T, as it were, or E over R is going to be equal to the big I, e to the minus R over LT. And they used voltage over resistance, the same thing as current. Let me just say this. Constant. And then you can instantly see here that this being a constant or amplitude or the max is going to decay exponentially from its max. And so coefficient, maximum value, and it's going to go, okay, like this, basically. And that is the universal current from max to 0. T goes to infinity. You can totally see that here. It's 1 e to the minus infinity as t goes to infinity. 1 over this is 0. And then t equals 0. This is 1 over e to the 0, which is 1, maximum value. 0 to infinity and beyond. Right? Goes to infinity. Makes sense? Any questions? So again, it goes all the way back to the beginning of everything when we're talking about how in a current that induces its own EMF, or an inductor put in a current, it's going to be responsible for increasing or decreasing current. Now that's going to be a gradual increase or decrease, and we've seen how this works. In the first case, where there's switch S1 is closed, we're going to have a gradual increase to a maximum. So thinking all the way back. Right, when this is closed and this is here, maximum gradual increase. Well, we have back EMF. Open this, even this is closed, doesn't matter. We're not even, it's not even, you know. That doesn't matter. Even though this is closed, there's going to be some part here. Just like we start with the RC, it's eventually going to die to 0 as it continues to make every turn. And then, you know, let's say that you let a circuit like, you know, here at B and it's now 4:30, 4:32, say by 9 o'clock, it's going to be basically 0. Some time has passed. So that's that. Any questions? We will continue, finish chapter 32 tomorrow.